is electromagnetic induction. The phenomenon of production of EMF, electromotive force, in a coil when the magnetic flux linked with the coil is changed is called electromagnetic induction. The phenomenon of production of electromotive force in a coil when the magnetic flux linked with the coil is changed is called electromagnetic induction. The EMF so produced is called induced EMF, and the resulting current is called induced current. Now, to understand more about this phenomenon of electromagnetic induction, let's first define what is magnetic flux. The total number of magnetic field lines crossing normally through a surface is called the magnetic flux, denoted by phi, linked with the surface. I repeat, the total number of magnetic field lines crossing normally through a surface is called the magnetic flux linked with the surface. If theta is the angle between the magnetic field induction vector B bar and the surface area vector A bar, you know that the surface area vector is taken normal to the plane of the surface, that is along the axis of the area, we take the area vector. So if theta is angle between the applied magnetic field induction vector B bar and the surface area vector A bar, then the magnetic flux linked with that surface is given such that phi equal to B bar dot A bar, which is equal to BA cos theta. The SI unit of magnetic flux is Weber and the CGS unit is Maxwell, and 1 Weber equal to 10 power 8 Maxwell. If a coil of N turns is placed in a magnetic field so that theta is angle between B bar and A bar, then the total flux through the coil, or the total flux linked with the coil, is such that phi coil equal to N into B bar dot A bar, that is NBA cos theta. So the magnetic flux linked with a coil is given such that phi equal to, or phi with coil, is N into B bar dot A bar, that is NBA cos theta, where N stands for number of turns with the coil, B is the field induction, A is the area of the coil, and theta is angle between B bar and A bar. And now, to understand a numerical expression for the electromagnetic induction, that is the EMF induced in a coil, so we have to study the Faraday's law of electromagnetic induction. Whenever the magnetic flux linked with a coil changes, we said an EMF is induced in the coil. The induced EMF lasts so long as the change in the magnetic flux continues, and the magnitude of the induced EMF in the coil is directly proportional to the rate of change of the magnetic flux linked with it, and it always opposes the change of the flux that causes it. The second statement is important. This we study more elaborately in Lenz's law. After this we understand that also. So here let's review it once again. The Faraday's law of electromagnetic induction says that whenever the magnetic flux linked with a coil changes, an EMF is induced with the coil. The induced EMF lasts so long as the change in the magnetic flux continues, and the magnitude of the induced EMF in the coil is directly proportional to the rate of change of magnetic flux linked with it, and it always opposes the change of the flux that causes it. So EMF with the coil is equal to minus d by dt of phi coil, that is equal to minus of the final flux linked with the coil minus initial flux linked with the coil divided by the time interval in which that change has taken place. Here in this expression, the negative sign is in accordance with Lenz's law. So in case of a coil of n turns, the phi coil we know NBA cos theta. Therefore, the EMF induced with the coil is equal to minus d by dt of NBA cos theta. So from this expression, for a coil of n turns, when placed in the changing magnetic field or the magnetic flux, EMF can be induced in three ways: by changing the strength of the magnetic field, that is B, by changing the area of the coil inside the field, and by changing the orientation of the coil with respect to the magnetic field, that is theta. So B may be changing, A may be changing, and theta may be changing. In any of the reasons, the EMF is possible with the coil.